next presenters. So it is from TAESIK GONG. Okay, please.
Hello, everyone. Thanks for coming. I'm TAESIK GONG from Bell Labs. Today, I'm very excited to present my work, DAPPER, Label-Free Performance Estimation after Personalization for Heterogeneous Mobile Sensing. And this work is done with my amazing collaborators, YEWON, ADIBA, YUNXIN, Seongju, JINWOO, and SJ. So let's get started. As a background, I will briefly explain what is domain shift and domain adaptation in mobile sensing. Domain shift refers to the distribution gap between the source domain and the target domain. And it's a well-known fact that while deep learning performs well under trained domains, it performs poorly under untrained domains. And this problem has been regarded as one of the major obstacles in realizing deep learning-based mobile sensing applications because their performance degrades a lot in a new domain, like a new user, new device, and their combinations. And domain adaptation is a technique where you can address this problem. And there have been many domain adaptation studies, such as utilizing some amount of unlabeled data from the target to adapt to the target domain, and utilizing some labeled data to adapt to the target. But what we notice here is there exists performance dynamics in domain adaptation for mobile sensing. What that means is there are so many diverse factors that affect the performance after domain adaptation, which makes the performance after adaptation totally unpredictable. And this is our motivating experiment with a human activity recognition data set and recent domain adaptation technique. And we varied 8 different factors. And as you can see, by changing a single factor like a target user, the adaptive performance varies a lot. And there are some factors that are user-related, such as mislabeling rate. Those are out of the developer's control. And also there are factors like learning rate, such as machine learning hyperparameters and so on. So by considering these multiple factors and real-world characteristics, these factors would interplay with each other, and it's difficult to guarantee the adaptive performance after adaptation. So our question is, how can you validate the performance after adaptation under this performance dynamics? Of course, there are some existing practices for performance validation, but there are limitations. The first most widely used method is train for a fixed number of epochs and select the last epoch's model, but this obviously has no performance validation and often falls into the following problems, such as the accuracy is now degraded after adaptation, and accuracy is now saturates too early so that the remaining training becomes unnecessary training overhead. And the best accuracy is observed in the middle of the training and leads to suboptimal performance. So to avoid this unnecessary or undesirable performance after adaptation, many studies use a holdout label test data to validate the performance after adaptation. But it's extremely costly and unrealistic to collect label data for every user for every different app. It requires users manual labeling effort to collect certain amount of high quality unlabeled target data and then validate the performance. It's unrealistic. So we now understand that performance validation is very important, but collecting label data for each user is very costly. So how can we validate the performance without any label data? That's our key question we'd like to answer in our paper. So we present DAPPER, Domain Adaptation Performance Estimator. And our intuition is in mobile sensing, unlabeled data could be collected naturally in the background sensing app. And our idea is to utilize such unlabeled data only to estimate the performance. So the objective of DAPPER is, as you can see, to make this estimated performance as close as possible to the ground truth accuracy calculated from the labeled data. then you might ask what kind of applications this performance estimation framework would have. There are many useful applications of this type of performance estimation. First, we can now improve the model accuracy because we can avoid model accuracy degradation. And at the same time, we can reduce the computational overhead by only stopping the model training when the accuracy is satisfactory. And we can also use this for model development and maintenance from the company's perspective. And we can also use this for designing user interactive adaptation because now user can understand the performance of the model. The user can initiate the model adaptation stage and then and the other way around, the system also initiate the model training, something like that. And our key hypothesis to make this possible, this adaptation and this performance estimation possible, is that there could be correlation between the model outputs on the unlabeled data and the actual model performance. So this is the overview of DAPPER. DAPPER consists of developer side and the user side. And in terms of technical contribution, I'd like to briefly explain two key enablers. The first enabler is mutual information for feature extraction. So our idea is based on information theory, and we identify the relationship between the information gain and the actual performance after adaptation. So we calculate this information gain between the inputs and the corresponding outputs of the model from the unlabeled data only. And this would be used as a features of the estimator and calculating the estimator performance. And the second component is we utilize simulated adaptation for training data generation. What that means is we utilize only the source data, collected source data, without additional data collection to train the performance estimator. So the source data is split into virtual source and virtual target. And we now, with this virtual source and target, we can generate a lot of simulated adaptation, and we can extract features that I mentioned, and also accuracies, ground truth accuracy. So we now utilize this amount of data set to train the performance estimator. So now let's move on to how DAPPER accurately estimate performance. These are some qualitative results. We show 3 cases where the accuracy is increasing, or the accuracy is decreasing, and also the accuracy is fluctuating. And the black solid line here shows the ground truth accuracy calculated from labeled data. And the red dotted line is our estimated performance. And as you can see that in overall, DAPPER shows the closest accuracy to the target label, which is Oracle. And here are some numerical highlights of the result. DAPPER could achieve 92 to 93% of similarity to the Oracle, with only 0.2% of extra computational overhead measured on off-the-shelf commodity devices. So this is the summary of DAPPER. We investigate the problem of uncertainty after adapting to the target domain, especially in heterogeneous mobile sensing where many real-world factors are interplaying. And as a solution, we present performance estimation framework called DAPPER with only unlabeled data. And the key intuition is there's a correlation between the model outputs and the model performance. And DAPPER achieved around 93% accuracy with 0.2% computational overhead. Thanks so much for listening, and I'll be happy to get any questions.
Thank you very much. So very interesting. Any questions from the audience? Okay, during changing the speakers, if you not. So I have one question. It is really interesting for me, and you are estimating some of the. Yeah, I think that you are also only using the unreliable data to model the performance or something. And can you apply to you in the title you have the personalization, but can you apply for other than personalization things for domain adaptation for something like a new environment, a new place, or this kind of thing?
Yeah, thank you for the question. That's very important point. So our motivation, the answer, the direct answer to the question is yes, it could be applied to a certain extent, although we are utilizing some personalization characteristics from the algorithm for the estimation. But our motivation of this study is usually the adaptation happens after deployment. So if we train a powerful model and we want to estimate the performance of the powerful models on the server, it's already usually have a certain amount of labeled test data to validate the model. That's the practice. So, yeah, the answer is yes, there is room to improve and estimate the performance for those other traditional deep learning performance validation.
Thanks a lot. So let's. Okay. So I have to announce that the next speaker has to cancel because of the visa issue. So we have to skip the next speaker presentation, which is